Hello everyone, I'm going to be telling you about centripetal acceleration today. So this is still to do with circular motion. Go on the previous video or really on the playlist on circular motion because you need to understand first what I mean with circular motion to be able to understand this new name for acceleration, okay, or this new type of acceleration you didn't know before. So centripetal acceleration. So first of all, remember that we are talking about a motion that is not linear. So there is a curve, okay? So the velocity of an object that is on circular motion is always changing, even if the speed is the same, because velocity is a vector. So that means that if you're going on a circular path or a curved path, your vector is changing. You are changing direction, even if the speed is the same, okay? So even if you have a constant speed, your object is going to accelerate, okay? Because acceleration is the rate of change of velocity. So even if the speed is the same, you do have acceleration because your velocity changes, because your direction is changing, okay? Now, the acceleration is always towards the center of the circular orbit, okay? And because it's going towards the center, we are going to call it centripetal acceleration, okay? And here it is, okay? So you have the object, that's where the acceleration is going, that's where the velocity is going. This ends up by doing a circular path, okay? So it's just, basic maths and vectors. So that's why you have a circular path. As you have learned before, for you to have circular motion, you need a force that is perpendicular to the velocity. And I will go into more detail on that force in a second, okay? And the velocity is along the tangent of the circle. So it's just about touching the circle, okay? Now let me just see this, so this part I already told you. So the place where the object is going to go towards, okay, so the direction of the acceleration is always the same as the direction of the resultant force, okay? And as I told you, in a couple of slides I'm going to explain this a little bit better. So, centripetal acceleration, it has a formula, okay? So A, the acceleration in meters per second squared, is equal to v squared, where v is the velocity in meters per second, divided by r, the radius of the circle or the curvature you're doing, even if it's not a full curvature, okay, in meters. So that's the centripetal acceleration. Now, because we're talking about circular motion, we should be talking about angular velocity, angular displacement. So I'm going to ask you, and obviously I'm going to show the answer straight away, for you to prove that the centripetal acceleration is going to be equal to omega squared, where omega is the angular velocity in radians per second, times r, where r, I didn't write it here, where r is the radius of the circle or the curvature in meters, okay? And it's really easy to demonstrate that. So acceleration is v squared over r. You already know from the previous video, and go there if you don't remember, that v, the velocity, the linear, equals the circular times r. So v equals omega r, because v squared, all of this is squared, divided by r, the radius of the curvature. So the r's cancel out, the square cancels out with the other r, so I end up by having that my centripetal acceleration is equal to omega squared, so the angular velocity squared, times r, the radius of the curvature. Now, you can always prove that A is equal to v squared over r. You will use a little bit of maths here, and you will use a little bit of geometry here. However, because you do not need this for A-level physics, and at the moment I'm giving priority to cover the whole course for anyone that wants to prepare for the exam, I am going to put this link where there is the proof in the description, and then you can click on this video and learn this by yourself, or learn this as an extra, okay? Once I'm done with all the videos, I can of course go and do some demonstrations for you, some demos for you, but that's not my priority at the moment. So remember when I told you I would tell you about this force? Here it is. So centripetal force, So it has to do with the centripetal acceleration, right? So you know that this is going to be the resultant force on an object in a circular motion, because you know that the acceleration is going to go in the same direction as the resultant force. The acceleration goes towards the center of the curved path, so is going to be called centripetal acceleration. You know that acceleration is going to be related with force and mass, so this resultant force will be called centripetal force. So is the resultant force on an object in circular motion, it is perpendicular to the velocity and it acts in the same direction as the centripetal acceleration. Because I have F equals ma, F is a vector, m is a scalar, a is a vector, so the two vectors need to go in the same direction, okay? And this is the rule that makes me have circular motion, having the force and the velocity perpendicular to each other. So here we have an example, a satellite, the planet Earth, or any other planet really if you want. The force of gravity, the velocity, and the result is that I'm going to have a circular path around the planet, okay? So, just, really quick exercises. I have 4 questions about the centripetal force that you have. So, for a satellite moving around the Earth, it's going to be the gravity. For a planet moving around the Sun, it's gravity as well. For an object attached to the end of a moving string, is going to be the tension on the string. And for electrons around the nucleus, is going to be the magnetic force. So, actually, you're going to learn, or you already have videos about this, I think. So you can have more than just one type of centripetal force, okay? Now, as I told you, F equals ma, that's Newton's second law, right? So I can now make the centripetal force in terms of the centripetal acceleration and in terms of the angular velocity. So since F equals ma, then F equals m times v squared over r, which is the centripetal acceleration. And I already know that v squared over r is omega squared r. So F, my centripetal force, can also be mass times my angular velocity in radians per second squared, and then square the angular velocity, okay? It's not the second squared, times the radius of my circle in meters, okay? So here's the formula, here's all the details. So mass, m is mass in kilograms, a is the acceleration in meters per second squared, v is the velocity in meters per second, r is the radius of the circle in meters, and omega is the angular velocity in radians per second. Now, this is going over something that I already told you, but let's just go over it again. So here we have circular motion, acceleration, perpendicular to the velocity. This is where the resultant force is as well, okay? So if the object is acted on by a single force, for example, the satellite around the Earth, that force is the centripetal force and causes the centripetal acceleration. So this is just reinforcing something that I told you. And then the centripetal force is at right angles to the direction of the object's velocity. This is one of the things that makes that we have circular motion. This is the thing that makes circular motion. So therefore, no work is done by the centripetal force on the object because there is no displacement in the direction of the force. Think about it. Work, by definition, is the force times the distance. So the displacement, and this is the distance in the direction of the force. Now the force is actually going in a different direction to the displacement, so there is no work being done, okay? The kinetic energy of the object is therefore constant because change in kinetic energy is the same as the work done, so the speed is unchanged. This is very important, okay? So think about it. No work is done because work equals force times the distance, and is going to be the distance in the direction of that force. Now, this is what I'm doing, but this is my force. So there is nothing in the direction of that force, so there is no work. Work happens to be the change of energy, and therefore the change of kinetic energy. But because no work is done, it means that the change of kinetic energy is zero, so that means that the kinetic energy is constant. Kinetic energy is equal to 1/2 times the mass times the velocity squared. So assuming that the mass is constant, because I should have the same object, the speed is going to be unchanged. Okay? Now, I'm not going to read all these questions, obviously, but these are some questions that you can try. All the information in this PowerPoint is going to help you getting the answers for these questions, and here are the answers for the questions, okay? If you have any problems, you can contact me, you already know that. So I'm going to end here. And I'm going to then do another video still on circular motion. Okay, so take care everyone. And oh, and by the way, if I think I still will do another video before I go away for a while, but you know that I will be in the hospital for a while, so just hang in there, and then another video will come up. You know, I don't know how long it's going to take, but it will come up. Okay, so take care, bye.